So now that we have this assembly code, that's great, but we need to do some stuff with it. Right now it's not very optimized, and for fun I decided to implement an optimizer class. So on the Commodore 32 compiler, once all the compiling stuff is done, it should be in the main function. Where is my compile function? Where's this end? Let's see here. Over here. That returns the assembly code. Let's see. I think we might do the here we are. Here we call the optimizer. We do it after every function, it would seem. Not very efficient optimizer. Basically, I just wanted to do this because real compilers do this. They basically go through the code, they try to find ways to improve it. Now my optimizer is terribly written. It goes through all the variables that it can, pretty much brute force, and it finds usages of them, and every time the variable is used, and if it's in a state it's already in, it will remove the instruction that tries to put it in the state it's already in, which optimizes it. And in the example program, I've done a pretty stupid thing. I've set var potato to 342, and then over here I set it to 342 again. And as you'll see in the assembly code, what it basically does, but the the optimizer basically goes through a lot of work to pretty much do that. It goes and sees variable 21, because by the way, compiler also assigns variable numbers. It'd be too complicated to understand that stuff. We got a memory map over here as well. Yeah, so that would be the first variable that we got. We have var potato. I wasn't very creative when I wrote this tutorial program thing, and basically that goes into the first RAM slot that's free, which is slot 21. So the assembly code will refer to slot 21. It'll basically replace var potato with 21 whenever it sees it, and that's also stored in the token attributes, by the way, the variable number. So that's convenient. When it's identified it as a variable, it replaces all of them with type variable, and it gives it the attribute 21, which tells it that's the address in memory. And pretty much it sees that this function has been used twice, so it comments it out. That's what the semicolon means. So that will basically make the code shorter, make the computer a bit faster. It was pretty obvious in this example, but in some cases it does actually happen. It does actually help significantly, particularly my number drawing program. It optimized a lot there because of how the GPU instructions work, and I actually wrote it in such a way that I sort of helped the optimizer notice ways to optimize it while still remaining very easy to read. So that's a really big advantage of the optimizer. Unfortunately, my optimizer is terribly written, and it basically just makes all sorts of assumptions. We've got some to-dos, and basically if it sees a branch flag, the chicken is out, and it doesn't bother checking where it's being used, because you know it could branch from anywhere. So it's just like, I give up, I'm not gonna bother checking that. But yeah, that's the optimizer. In real compiler it's a bit more complicated, and it does optimize during the Lexer stage, where it parses the tokens. I'm using all sorts of fancy words, I'm sorry. Okay, so once we have this, we will have our assembly code. So we should eventually get this compiled code, and okay, so that would be called by the compiler method. I don't remember what it calls it. It's called in a bunch of places. If we chose upload, remember? So now this is done. We get that into current, and because we don't have a break here, I'm using some clever coding strategies here. We can assemble it, and so we take that, store it in temp, then we assemble current in temp. I did this because I was having some variable problems. I never bothered putting it back, it seems. But yeah, so we have this code, and we need to turn it into instructions that Commodore 32 will recognize. Well, these are Commodore 32 instructions, but they're not in the format it recognizes them in. And there's also branch flags, because what the compiler does is whenever it needs to jump somewhere in the code, it plonks this little branch flag. Even if it doesn't need branch there, it puts the branch flag there just in case it does need to eventually. It doesn't matter, these don't actually take up code. And it says, okay assembler, you worry about what line that's actually at. And the assembler, it's got two stages. So this isn't actually assembler, this is still the GUI class, this is the assembly error catching system. We construct it, we assemble. Here's the assembler. So, two stages: find and replace goto markers, and convert the assembly code. So, the find and replace goto markers pretty much goes through the code. It counts how many lines we've gotten. This is a commented out line, so it doesn't count that. And it sees a branch flag. It puts that in memory into a little lookup table. I should have probably used a hash map. For the lookup table, I didn't. I'm sorry. That would have probably been much more appropriate than whatever the solution I decided to use here. Alright, I pretty much, whenever I found a branch flag, I would find all usages of that branch flag. So I'd go over here. Here's where they use loop 0, and I'll replace it with whatever line number it is, which would be 1, 2, 3, let's say. And it would remove the branch flag from the code. But we're not going to do that. That's what the assembler does. I'm not sure if you can see the output. Should output it somewhere. Final main optimized code. No, that's still got the branch flags in it. Never mind. Anyways, that's what this thing does. It finds them, counts how many valid lines there are, and it labels. It gets the branch flag labels. And then over here, we take the code and we actually convert it into what the Commando 32, or what will be used to upload it to the Commando 32 rather, the scoreboard set commands. Now, in Minecraft, there's some scoreboard commands you can type that will change, well, the value of the scores. And it pretty much uses those to change the code in the program. We'll explain how this actually gets onto the computer later, but pretty much the assembler is responsible for converting it to those numbers. There's 3 numbers per instruction. One for ROM A, one for ROM B, one for ROM C. ROM A stores the instruction type, what it does. ROM B and C store some extra information. So for the first command we have here is store 34221. Each of these commands will have at most 2 arguments. If they don't, like this debug print, this is actually the print function. If it doesn't have a second argument, it'll just get a 0, because we're still going to set it to 0 in case it's important. So over here we've got a reference sheet, and you'll see that the store command over here, it's number 6. It takes in a constant value and a destination address, and what it does is it copies value of A, argument A, to address B, which is the destination address that it takes in. So it basically takes number in A and stores it at address B. So number in A, the 342, we're storing it at address 21, which, as we saw, was the first RAM line, and as you can see, it's the first variable, so it'd be logical if it were assigned the first slot in RAM. And as you see, we're assigning it the value 342, so this instruction makes perfect sense. And in the machine code, you'll see 6, 342, 21 as ROM A, B, and C respectively. So yeah, that's all the assembler really does. It doesn't do as much as the compiler does. It pretty much directly translates things, but it does do branch flags, which is super important step that it needs to do that the compiler doesn't, because if the compiler were to care about what lines things were, keep track of that, it actually can't, because of how everything works in layers and sort of recursively works when you're recursively putting parentheses in. So that would be like 3 functions calls, and probably be a bit more because of all the other stuff I do. I don't know how many it actually is, but yeah, this pretty much converts each line. Each line corresponds to a single instruction, whereas in the high-level language, a single line could just equal like 10 assembly instructions, I'm not sure how much the actual number is. I know GPU instructions take up quite a bit, especially because they take in a lot of arguments, and those are all stored in memory. So yeah, when you have like GPU instructions, what the compiler will actually do is it will store them in special places in memory. Slots 4, 5, 6, and 7 in RAM. Store the X, the Y, the X, and the Y for 2 coordinates. And we have this color register as well, or color variable, special variable, which stores the default color. That's where it stores it. And then we have this temp register, which is used by the compiler for swapping variables and temporary assignments and sorts of things. So yeah, these are for math as well. It needs to store them to those to do math. And yeah, that's how the assembler basically works. It doesn't do that much, but its job is pretty important. It does like convert these statements into what numbers they are, and there's a big old table over here. As you can see, this over here, we've got some compatibility mode stuff. I don't know why I bothered keeping them in there, maybe because I'm lazy and didn't bother taking them out, but some of the old programs I wrote in assembly are still there. Also, I bothered replacing all the color types because I used to code in assembly before I got the compiler working to test the computer while I was building it. If you look at my old videos, you'll see that. And this basically makes it easier. It pretty much converts the register names, like x1 to 4. So every time you used, if I used x1 in here, for example, instead of the number, it would, why am I looking in here? It's in the Excel document. It would swap it for address 4 and swap it for the number 4. That's pretty much what this does. It's a big formatting thing. It removes comments as well. Converts everything to uppercase because it's not case sensitive, so I just work with everything in uppercase, which is why this is all capital letters. You can use lowercase if you want, but you know, assembly usually isn't case sensitive. So yeah, converts to scoreboard commands. I think I've explained that enough times. So yeah, we got 2 passes for go to and converting. So once we've got that done, we'd be in the assemble command. Where's the assembly command used? In the upload. So we're still here in the method when you push the compile button. So we're back here. So what this did was convert to assembly, and this converted it to machine code, which is this stuff. Now we need to get it onto the computer. This is where things get a little interesting. So if still go, which basically means has anything failed, then our write buffer is equal to current, which is our instructions that we have that I just showed you, the scoreboard set commands. And then we click or do start assembly, and we'll do that only if there's no issues, of course. We don't upload code if it didn't work. And what start assembly does is it sets time until start, and we've got this little loop thing here, and this pretty much starts the progress bar. So when you've got this little program, you've noticed the progress bar goes like this. That's the 3-second countdown in which you have to select the Minecraft window for the uploading process to begin. Once you select the Minecraft window, so time until start gets to 0, it'll start the uploading process, and this basically in charge of timing and stuff while still keeping the interface updating, so we have that nice progress bar telling us how much of the work is done. I'm not sure if I should perhaps use the uploader for this, because this is basically a simplified version of this. So here this is a much simpler version. It doesn't use threads and loops and all that complicated stuff that we need to use for swing, which by the way is the GUI manager thing. Don't worry about that. We just do thread.sleep 3000. Just go to sleep for 3000 milliseconds, 3 seconds, and we go through the file. This basically, the first time is to check for errors. If no errors happen, then as you can see, we check if it's a valid program. Then we wait, and then we upload it. And this true flag means that it's a real run. This is pretty much the same that happens here, except it's a bit more complicated, as you can see, because we got some progress bars. updating and stuff, and we got all sorts of commented out code because I wrote that first before this one. This is a cleaned up version of that. And we exit with a little error code. And yeah, this goes to the keyboard class, which we also have in the this one. You can see keyboard class is over there. It's the same thing. We do tcom, which I don't know where tcom is. Tcom's over here. I call tcom text because my code is terrible. And this is pretty much what it does. There's 2 steps to getting this code onto here. So now we've waited 3 seconds. We assume the user has now selected the Minecraft window. We don't have any way of checking, and we need to get this into the Minecraft universe. These instructions, and we need to get them onto the computer, the command 32. So what we do is we type the letter T, and what this basically does is we get a big. I should replace this one day. This is how I used to upload code, with this big switch statement thing, but now I've got a different method because it's faster now. We push the letter T on the keyboard. We've got this virtual keyboard system going here. That's the Java robot class. Very interesting class. Allows you to emulate a human. So we are pretending to be a human here, pushing the letter G on the keyboard, which then Minecraft goes, okay, you opened the text menu to type some text. And now what we do, while we wait for Minecraft to open the text dialog, because it takes a little while, it takes a frame, runs at like 30-60 frames per second, depending on how good your computer is. So it's going to take a while. Meanwhile, we're going to set the clipboard. So what we basically do, this takes the system clipboard and it sets the contents to our command. So this is interesting because when you copy paste something, Control C or right click copy, or then you can go to any window you want. You can go to open this and you can paste it. You can copy paste between different programs. It's this wonderful thing. I'm pretty sure you've used copy paste before. You know, it works between windows. It's great, and that's what we're going to use here. We're going to exploit that. So what we're going to do is we're going to set the copy buffer, the clipboard, the system clipboard, and we're going to set it to the command we're uploading. So we'll do one command at a time. We're going to take, so let's do the first one. We're going to put this, we're going to copy this. That's pretty much what it's doing. It's putting it into the clipboard, and it's going to select the Minecraft window. I don't have Minecraft here. And it's going to do, we don't actually have to physically select text and copy it. This just lets us access the system clipboard, which is a very convenient version of that. So what we're going to do is we're going to select the window. Users already select the window, and what we're going to do, this is some more stuff. This is basically to check if our copy paste has worked. It's because we got nothing better to do while we wait. Then we open sleep. This is just waiting for Minecraft to respond, and then what we do is we push Control and V. Now that's the paste command. Control V. Then we wait, see if there's any errors. I don't know what this is actually here for. Then we release Control and V. So, because we're still holding them down. The reason we're not pushing Control, letting go, pushing V and Control, and pushing Control, letting go, V and letting go, because that just types the letter V. We need to hold them down. So that's what why this is a bit more complicated than pushing letter T, because that's you just push it and you release it. For this, we need to keep them down. And then we push the enter button. You know what that does when you're in the Minecraft chat window. So we've opened the Minecraft chat window with T. So that opens the chat window. We push paste, and then we push enter. And that, of course, types the command into Minecraft. You push enter, Minecraft executes the command. And because this is a scoreboard players set command, we are setting player 0 in scoreboard ROM A, their score to 6. And that is how we get the code onto the Minecraft computer. And then over here we've got another delay. It's close sleep. It's pretty much waiting for Minecraft to close the little box thing. And we've got a lot of delays because what we're doing here is we're emulating a human. And humans are incredibly slow. And computers just assume that we're slow. So it's like, oh, we don't need to worry. They're not going to type that fast anyway. They're not going to type 1,000 letters a second because no one types that fast. But because we're emulating a user here and we're doing it at like 1,000,000 instructions per second, we can type 1,000 characters per second if we so wish. We could easily do that. In fact, that's be the default. But we need to wait because the program's going to expect the user to be slow, and you know, so that's kind of a problem when trying to be a human, because humans are such slow things. It's terrible. We should be faster. Programs should assume we're faster. So yeah, that's what all the delays are for, and that's why uploading's so slow. Because if you increase these delays, then things go wrong because it's not used to things being typed in that fast, because, you know, humans. And that's the entire uploading procedure, I guess. We've got some other functions as well. We've got the drag and drop window. Oh, wait, this is the uploader. Sorry. Yeah, that's Java result 1 is you did select a file. Java result 2 is you select a file, but it's not a program. I meant to run the compiler, which is this one. You've got gen assembly, gen machine code, which basically this will only run the compiler. It doesn't run the assembler, so you have the assembly code. That's pretty much how I got this. And gen machine code runs the compiler and the assembler, unless you select assembly here, in which case it doesn't run the compiler because it's already assembled. Well, it's already generated assembly code. And machine code, you can upload that. And then we have the commands to clipboard. What this does is it pretty much, instead of typing all the commands in, it puts all the commands into the clipboard. So I'm going to just select the file, simple program, commands to clipboard, make a new one. If you push paste, it'll paste all these commands. You also notice that all the slashes are missing at the front. This is intentional. This is if you have a server, a Minecraft server, you paste this in and it will execute all the commands, because this goes into like a standard input stream, which conveniently for us is actually designed for both humans and machines. So it's designed to take in multiple inputs, take in a giant file read at 2 million bits per second. It'll be fine with that. It'll handle that perfectly, and it takes it into the standard input stream and it runs it instantaneously because it's designed for computers and computers are fast. So that's the big advantage to using that feature. It's not that complicated. I don't think I need to explain it. It just removes the slashes, puts the whole thing into the clipboard, which is pretty much the code we had over here. Go away. Over here. I'm not sure if I verify when copying to clipboard. I might, but I don't think I do. And you just tell the user, go paste that into the server window, and you'll have your program on. It'll just execute the scoreboard set commands, set the scoreboards, and then it'll be available for the Commando 32 to access the instruction numbers, so it can read them. If you want to know how these instruction numbers work, how it reads these instructions, because I haven't actually explained that, it's intentionally haven't, because I'm going to explain that in the other video. I was going to explain that, I was going to explain in the video a little later as well. But, yeah, if you want to know how it reads them from the scoreboards and how it recognizes them, how it knows what to do with them, you're going to need to watch my Commando 32 explanation series for the computer, because this was just for the compiler and how it gets it onto the computer. So now it's on the computer, now the computer just needs to read it and run it. But that's for another series, another Commando 32 how it works series. If it's done, there will be a link in the description. If it's not done yet, which probably isn't if you're watching this now, but well, actually you might be watching this much later and it won't be done, but yeah, just go check the description for that. And thank you for watching this. I hope I made it clear how the compiler and stuff works, and bye.